Okay, so now we're going to do a few exercises. For example, let's just say that you got a differential equation in the format y double prime, so it's the second derivative of y minus y equal to 0, okay? This is an expression, and I want to find out what the solution for this expression is. Of course, you're not going to be able to find just from this. There are many solutions to this, okay? And the exercise just gives you a few other equations and asks you if these equations fit this thing right here. I mean, if you, for example, you're going to be given, for example, f of x, and then you take the second derivative of the f of x, okay? You plug this in here, you plug the f of x in here and see if it's going to be equal to 0. If it's equal to 0, this equation is one of the solutions of this. This has many different solutions, okay? So the equation, let me just see one thing, okay. The equation y equals sine of x. Is that a solution for this? Well, let's see. Y prime equals cosine of x. Y double prime equals minus sine of x. Now we plug it in. So it's going to be minus sine of x minus, because this sine, minus sine of x was put in here. Okay, and then you have this minus, which is in here. And you put the y. Y is this. So it's going to be minus sine of x. This equals minus 2 sine of x. This is not always 0. I mean, there's just going to be 0 when x is like n pi, okay? And n, yeah, n can be an integer. So for example, 0 pi, 1 pi, 2 pi, 3 pi, all these are going to be equal to 0, but is minus 2 sine of x always going to be equal to 0 for any x? No. So this equation here does not satisfy this one. Okay? This equation does not satisfy this differential equation. So let's try again. Y equals 4 to the e to the minus x. Yeah, 4 times e to the minus x. So the first derivative is going to be equal to minus 4e to the minus x, right? Because e to the minus x is e to the minus x. The 4 is just repeating because it's a constant, times the derivative of this, which is minus 1. So you get that. The second derivative is going to be equal to 4e to the minus x. So let's do it. 4e to the minus x minus 4e to the minus x, is that equal to 0? Yes. So this equation here fits, is one of the solutions of this differential equation, right? This expression here, this function, this y, is one of the solutions for this differential equation. Okay. Let's try the third one. The third one is y equals c times e to the x. C is a constant. So let's see. First derivative equals c e to the x. The second derivative equals c e to the x. Plugging it in, so you have c times e to the x minus c times e to the x equals, is that equal to 0? Yes, it is. So c times e to the x is another solution for this. Okay? Now, here's another example. I'm telling you that, well, let's, this is a function of time, okay? This is a function of the space with respect to time. If you take the derivative of this, of course the derivative has to be with respect to time. You have the velocity, right? And if you take the derivative of the velocity, you have the acceleration. All of these is with respect to time, okay? So what I did was to put this in here. This equals the derivative of the function of space with respect of space as a function of time with respect to time. This is the same thing as the derivative of the velocity of the function of t with respect to time. Okay, so there you go, you got all these things in here. Now I'm telling you that this here, let's see, this thing equals minus 32. Minus 32 was probably feet squared per second, or feet per second squared, yeah. So you have that. So in order to find the function for the velocity as a function of time, you want to integrate this stuff. So it's going to be minus 32. You want to integrate it with respect to time. So it's going to be minus 32 plus C1. Okay? And now if you want to find the function of the space as a function of time, you integrate this one with respect to time again. So minus 32t is going to be minus 32t squared divided by 2, which is going to be minus 16t squared. Okay, plus c1t plus c2. All right, and now I'm going to give you initial conditions. I'm going to say that the s of 0 is equal to 80, right? If I'm telling you that the s of 0 is equal to 80, if you put a 0 here, you knock out this term and you knock out that term. That means that c2 is equal to 80, okay? So I'm going to erase this stuff and I'm already going to put an 80 here. All right? And I'm telling you also that the s prime of 0 equals 64, okay? What does that mean? That means that the initial position is 80 feet at the time 0, and the initial velocity at the time 0 is 64 feet per second. So if you plug this value, if you plug this thing in here, okay, this is going to be a 0, so this is going to be knocked out, so C1 is 64. So I'm going to erase this stuff in here. I'm going to erase it in here. I'm going to put a 64 in its place. And there you go. Now you have this function, right? The function of space is a function of time equals minus 16t squared plus 64t plus 80. All right. I'm not trying to do that. Make this little noise go away. So you have x, y prime, minus 3y is equal to 0. Now verify that c to the x cubed is a solution. Well, let's see. If y equals c to the x cubed, y prime is 3c to the x squared, right? Well, let's do that. X times c3 to the x squared is going to be times 3c to the x squared is going to be 3c to the x cubed minus 3y, which is going to be 3c to the x cubed is equal to 0. Is that equal to 0? Yes, it is. 3cx cubed minus 3cx cubed equal to 0. Okay, so we've done that. We verified that this function here is a solution for this differential equation. And find a particular solution determined by the initial condition y is equal to 1 when x is equal to minus 3. So it's saying that if you put minus 3, y is equal to 2. Yeah, y has to be equal to 2. All right. So let's do this in here. So it's going to be 2 is equal to c x, which is minus 3 cubed. That means minus 27x, minus 27, right? That means that c equals minus 2 divided by 27. So this function here becomes y equals minus 2 divided by 27 times x cubed. That's the original function. That's the solution. Okay. Now, here's another exercise. Here. And, you know, this thing is just asking you for the solution that, for something that kind of fits this. This is a field of slopes, okay? So you see that here when x is equal to 0, the slope is going to be equal to 0. All right? What about here, for example, as you keep coming, so as the x increases, the slope is going to increase. As x decreases, the slope is going to decrease. You see that for an x that doesn't change, it doesn't matter what the value of y is, so the slope does not depend on y, okay? It doesn't depend on the value of y. See, it's the same. It just depends on the value of x, okay? So let's see. Well, I'm going to write this down. It's better. The solution here, y prime equals x plus y. Does that fit in here? No, it doesn't, because y prime is the first derivative of y with respect to x. Okay, this thing equals dy dx, which is the slope. It's the angular coefficient of whatever point. Okay. So this thing is going to depend on x and y. We just determined that in this slope field in here, the slopes don't depend on y, so it can't be this. This is wrong. What about y prime equals y? No, we just said that it doesn't depend on y, so this is wrong too. Y prime equals x. Yes, this one fits in here. Okay, because it depends on x. When x is 0, the slope is going to be 0. When x increases, the slope is going to increase as x increases. When x decreases, the slope is going to decrease as x decreases. So that's another thing in there. Let me see. Now a new one. Here. Here. Let's evaluate this slope field in here, okay? So when x changes, the slope is increasing, so it depends on x, okay? When y changes, also, but x doesn't change, so you see when x changes without y changing, it's varying according to x. When y is changing for the positive, the slope is becoming positive. When it's changing for the negative, the slope is becoming negative, okay? And over here, for example, you have one positive and you have a 1 in the y, which is also positive, so you get a slope of 2, okay? Over here in this part, you can see that you have a slope of 1 because of x, but a slope of minus 1 because of y, so 1 minus 1 is 0. You can see that this is 0 here, okay? And this is the same thing, it's 0 over here. So you see that the slope field depends on the value of x and on the value of y. So you can say that the sloping field in here, the slope depends on x plus y, okay? This condition fits this slope field. Let's try the third one. So as x changes, nothing is changing, okay? Yeah, you can see that all across the x doesn't change. There you go. But when y changes, it increases. When y increases, the slope increases. When y decreases, the slope decreases. So you know that the The differential equation that fits the slope field is this one. Y prime equals y. Okay? And that'll be it for this video, guys. I'll see you guys in the next one.